Okay. Good morning, everyone. The weather is not so nice as yesterday, so it's good for you to follow this lecture. One motivation more to stay at home and listen this, I hope, interesting issues about ocean variability. We may remember last lecture was devoted to the one of the most important mechanism of interannual variability that influence not only its region, namely the El Niño, La Niña, or better, the El Niño ENSO variability that is takes place in the Equatorial Pacific. This is a complex system that combines the mutual interaction between atmosphere and ocean. And most probably, this phenomenon has been already discussed about atmospheric dynamics. And that's why I focus more on the ocean component. So I speak often about El Niño, La Niña, just because this means that my interest is, my expertise also is related to the ocean. But I cannot forget to mention that the atmosphere plays a major role in developing, maintaining, and closing this this phenomenon. You may remember we have two extreme states. One is El Niño, the other one, the opposite one, is La Niña. There are many manifestations of these two extreme states, but the most striking one is the very clear, cold tongue in temperature anomaly at the Equatorial Pacific for La Niña, and a very prominent signature in the same area, positive anomaly in the Equatorial Pacific for El Niño. So there is a change of polarity of this SST pattern. I think it's important to state and to discuss a bit the fact that the two states, El Niño and La Niña, tend to self-stabilize, or even better, self-amplify, because there is a positive feedback process between atmosphere and ocean in each state. This explains, or may explain, also the fact that when El Niño is established, its duration is quite long compared to the seasonal variability. This is that, well, the general mode of variability also in the tropic, and the same for La Niña. And which is the mechanism? Let's give a look to this very simplified cartoon. We have a east cool region that is in the Pacific area, as along the Peru coast, and there is a warm region in the ocean. It's a warm water pool that is this rims the Australian New Guinea coasts, and the two are connected by atmospheric cell. There's a above the ocean, the trade wind, and have the return air flux to the Walker cell. Walker cell has zonal shape that goes just around above the equator. Let's examine in detail how the Walker cell contribute to sustain and to amplify the El Niño phenomenon. If you have stronger, having this temperature gradient, we have also an exchange with the atmosphere, and so the air above the Peru coast is cooler than the western part, so the pressure gradient is high, and we can remember we are at the equator, so the trade wind goes almost parallel to the equator, and when the gradient is higher, SST gradient is also higher, and the trade wind is increased, and the Walker cell walk even better. Strong wind means strong evaporation, strong upwelling, and this means that the stronger the wind, the stronger the Walker cell, the stronger the pressure gradient, and the stronger the difference in SST. So this is one case in which Walker cell increase this. In case if you have a weakening of the trade wind, this is the typical El Niño condition. The zonal SST gradient decrease for the same reason that we have said before, and also the whole Walker cell decrease its intensity and energy. And the trade winds at the equator slow down. This means that less evaporation, less upwelling, and the El Niño pattern clearly emerge. So we have the two situations that are, it's the first is La Niña, the second one is El Niño, that are sample amplifying and self-stabilizing. That's what this explains the fact that, or may explain the fact that the stability of the pattern is longer or less influenced by the seasonal variability. Okay. We talk about water masses, we talk about temperature and SST temperature and exchange with atmosphere. But now we want to go more into detail to the physics of the ocean that is involved in this mechanism. And as you may remember, the scale of the Pacific Ocean is so big that most probably advection of the masses to justify the changes in thermocline or upwelling and so on is not, well, the proper scale for that. And this intuition is true. The oscillation of the thermocline depth anomaly, which is the basic mechanism that favor upwelling on the Peru coast and create the warm water pool on the west part, is created by baroclinic waves. Essentially, we have the equatorial Kelvin waves that propagate quickly eastward, and quickly, relatively speaking, you have To remember, the equatorial curving waves are baroclinics or are largely driven by the as a return force or restoring force by the reduced gravity, which that's explaining the fact that the crossing time is about 70 days. So, and we have a return wave, which is the off equatorial Rossby waves that are moving slowly westward, about 200 days. So what is important to keep in mind here, that has an asymmetry in the velocity, and in this zone of the major waves involved in propagating and mediating the perturbation of the thermocline along the equator. I would like to refresh a bit what are the characteristics of equatorial waves, curving waves. You may have already touched this topic in Ricardo lecture, but it's not bad to go back and refresh a bit our idea on that. Equatorial waves are baroclinic waves. I mean that they are the intensity varies with the depth, and they propagate all over the water column, but they are more intense as a thermocline. So if you want to capture the signal, if you look at the thermocline and you have very clear signature of the passage, for example, of the transit of the Kelvin wave, while in surface, the signature may be less intense. Which are how the equatorial Kelvin wave are sustain themselves. You may remember the Kelvin waves need to have a coast, and the Coriolis work to keep the pressure gradient due to the slope near the coast with a return force, which is the Coriolis. In this case, we don't have any coast. We have two different flank of the waves, and each of them creates, just because of the difference of height, a pressure gradient. We are in a rotating reference system, so Coriolis is acting, and this is in geostrophic in equilibrium. The funny thing is that the Coriolis force changes according the hemisphere. So we have two different forces due to Coriolis on the northern part and southern part, and northern part, and they have the same intensity when you have the same slope, but the opposite sign. So the meridian balance between Coriolis force and pressure gradient is opposite side in the two hemispheres. And that's why this explains why this is really connected only to the equator. And the fact that the Coriolis force is depending on the velocity, and explain the fact that the propagation only eastwards. You cannot have equatorial Kelvin waves going on the other side. Why? Because the Coriolis force, in this case, if the propagation is on the opposite side, will not counterbalance the pressure gradient. We have the same intensity, but the direction at the verse the opposite. So we wouldn't have any balance between pressure gradient and Coriolis going westward. So this is one specific feature that is good to keep in mind. And as we saw earlier, the blue arrows are the Kelvin waves. And how far they propagate. And as in the case of the coastal Kelvin wave, the typical scale is the Rossby radius of the formation. You see here, this is the phase velocity of the wave in the thermocline. As I told you, what is the story forcing is the reduced gravity, which is the gravity acceleration modulated by the difference of the density between the two layers, the upper layer, the lower layer, that has created the interface, the thermocline, for example, in which the wave propagates, and h is the depth of this layer. So this should be very well known, and the scale is ordered 200, 250 kilometers. This means that the whole equatorial waves encompasses in 500 kilometers, and outside their effects vanish. And that's why this kind of waves are called chapel. I mentioned Kelvin waves, and I mentioned Rossby waves. So I would just to rehearse a bit what Rossby waves are. Rossby waves appear when a gradient of potential vorticity exists. You remember that the potential vorticity is obtained as the sum of the planetary vorticity, F, or Coriolis coefficient, and Z, which is the local vorticity, the vorticity of the fluid, divided by H, which is the depth of the layer, or the depth of the water. Obviously, you can have Rossby wave due to changes in H. So there are topography Rossby waves where topography can have an impact. But in the case that we are looking for, the changes of the potential vorticity or the gradient is depending on the meridian variation of the Coriolis coefficient. So Coriolis coefficient is 0 at the equator, but his change, his gradient, is the highest, and at the equator. So little changes in the latitude has relatively important changes in F. And this is called the beta effect. Beta dub the first derivative of the Coriolis with the term with latitude. And this is quite important kind of wave that can be found both in atmosphere and the ocean. And also in our case, the Rossby waves that are interested and are baroclinic Rossby waves, whose phase velocity is always westward in zonal direction. So we have two kinds of waves, one going eastward in the Equatorial Pacific, and the other one that can go westward. And the phase velocity is always westward, but the group velocity, the velocity that moves the energy, depends on the wave number. For small zonal wave number, the group velocity is westward. Instead, for large wave numbers, so shorter, relatively shorter Rossby waves, is eastward. Again, the Rossby waves are baroclinic, and they are small. At the oscillation is small along the ocean surface, and are large along the steeper thermocline. And you see here, there is a cartoon. It's not in scale, but just to give an information. The oscillation at surface is small, in the thermocline much larger, or 100 meter, and the wavelength is very, very large. You can have about more than 1,000 kilometers. And the speed is quite low. I told you that the Rossby waves takes 200 days to cross the ocean. So the order of magnitude of velocity is less than one meter per second. So they are very low, slow, the slowest wave in the ocean, probably. And the Rossby waves are approximately transverse. I mean that the velocity is along the wave crest, is perpendicular to the wave vector. And this means that most probably the geostropically waves are in geostrophic balance more or less as the equatorial wave do. This is just to recall some basic features of the Rossby waves and the equatorial Kelvin waves. Also, Rossby waves can have a specific formulation for equator, also because F vanish at the equator. We have one, let's say, flavor of the Rossby wave also for the equatorial region. Let's go back to the previous cartoon, and we can now give a better understanding of what happened here. So essentially, we assume that there is to start the mechanism, for example, El Niño, you should have a perturbation in atmosphere approximately here in the western part of the ocean. And there is a wind anomaly on the equator. And this wind anomaly creates or leads to a local thickening of thermocline. So the energy should start from some part of the atmosphere, and this is transferred locally in the thermocline. When the forcing is over, you have a displacement of the thermocline, and this thermocline tends to return to its say previous pristine state by emitting two trains of waves. Unfortunately, the two trains of waves cannot be of the same nature, because we remember, or may remember well, that the Kelvin waves goes only eastward, while the Rossby wave can go westward. It's interesting to remember that the Kelvin waves are strictly connected to the equator, so equatorial. In the Rossby waves that are generated here are near the equator but are off the equator. So because obviously the dimension, the size of the perturbation cannot be conceived as only at the equator. It has some special dimension that obviously include the equator and its surrounding. So the Kelvin waves propagate eastward and carry the anomaly in the thermocline west and sorry, that's an error. It goes eastward, not westward, and it takes sometimes order of 70 days, and when the Kelvin waves impinges the Peru coast, part of the energy is deflected northward and southward as a coastal Kelvin wave. The two Kelvin waves propagate poleward, subtracting part of the energy. The rest of the energy is reflected, but surely, in this case, we cannot have again a Kelvin wave. The Kelvin wave goes only eastward. Then the reflection is obtained by a Rossby wave. The Rossby wave that is generated here also takes more time, but hits the shelf of Australia and New Guinea here, and it's also reflected, giving way to a Kelvin wave that propagate back, and this is more or less the wave mechanism that is behind of the oscillation of the thermocline. What is important to note is the fact that this process can take place only at the equator. So there are many peculiarities that say this, that explain the fact that the El Niño, La Niña takes place only at the equator. Probably the most elegant explanation is the fact that in the reflection is possible only at the equator, because at the equator, Rossby and Kelvin waves can have the same frequency as this is required for equation. And and at mid latitude there are quite well. It's a difference in the frequency between the two. So the reflection is no longer possible. To justify this, I'll show you this graph, which is a very famous one. I took from Vallis, but there are other sources in literature that show the the graph that relates k, which is the wave number, with the angular frequency omega. And this represents essentially the dispersion relation between the two key variable of the wave. So their spatial dimension and the time dimension. And you can have here plenty of different kinds of wave from the inertial gravity. There's a family of inertial gravity which are higher in omega and which are cannot be related to Rossby Kelvin, and they come from a solution of an equation which has an infinite number of it's a family of meridional modes, and which is and every mode is associated to an integer index n. For zero particular case, which is called mixed Rossby gravity wave or Yane wave, and below below this horizon, you have two kinds of waves: the Kelvin and the Rossby. Both of them as similar in this area, similar angular frequency, similar wave number, and this means that this can pave the way for the reflection. And you have here the equatorial sorry, I have a bit of problems here. And we have the equatorial Rossby wave dispersion relation that, as we know, put in relation the angular frequency and the wave number. Omega is the angular frequency, k is the wave number, beta is the beta term, so is the the meridional derivative of Coriolis term, and c is the phase velocity of the Kelvin wave. So it depends. It depends on beta for the wave number and the angular frequency. Sorry, I have a little problem with my screen. Okay, hope to have solved it. So, sorry. And again, we have a family or Rossby waves that depends on integer number n. What is interesting to see here that the group velocity, while the phase velocity in this dispersion relation graph is given by the ratio between omega over k. The group velocity is the derivative of omega with respect the derivative of omega with respect of k. That geometrically means that this group velocity is related to the slope of the Rossby wave. So the Rossby wave has a little hump here, so we have negative and positive, and this explain or justify the fact that we said that the group wider than the ratio between omega over k is always a negative. Rossby waves propagate westward, as you can easily guess looking at the dispersion relation graph. All the Rossby waves are on the negative k, so the ratio will be always negative. And group velocity is not so monotonic, have positive and negative here. You can, obviously the scale should be enlarged, but we can have both of them. So we have already somehow analyzed the basic mechanism which are explain the ocean response to the ENS phenomenon. And we understood that what is important is to capture the basic feature of the wave propagation in order to give at least a formal explanation for this process. And obviously, there were many different attempts to do that. Probably the simplest one is the representation of the ENSO in terms of an oscillator. You can imagine to have successive state of El Niño and La Niña as a two extreme state of oscillating system. So we have the downward Kelvin wave and the Rossby waves. They go in opposite direction, hit the boundary. One is reflected, and this have an effect on the wind stress, and this seesaw behavior can be represented by an oscillator. The key aspect for giving a more realistic flavor to this equation is the fact that two waves have different velocity. And also, it takes time in order to travel across the basin. So the equation is that try to describe the system is set in terms of variability of the temperature and at the eastern part of the basin. And so it's something that depends on the temperature itself. And T is the C evolution of the temperature anomaly. And beta, B is a negative feedback delay in time. And this is a term that depends, a stabilizing term that takes explain for the dissipation. Let's give a look more into detail to these terms. So we want to see what is the changes in the temperature anomaly on the eastern side. We have a local wind positive feedback, which is AT, a positive SST anomaly in the East Pacific. That's which is connected to the changes in eastward wind stress Kelvin waves, as we told you, and deepening thermocline, warming, which is, this is essentially the positive wind wind feedback due to the Walker-Self mechanism that we discussed earlier. Then we have the delayed negative feedback and the wind stress current anomaly that creates off the equatorial thermocline shadowing and westward propagation of Rossby wave. So the two concepts that we saw before are encompassed here in A minus B. The two terms are account for both of the energy propagation, one positive, the other was negative. And the difference is, the key issue is the delta factor, which is the delay. The term is a non-linear damping term that includes all the dissipative phenomenon is a sort of a trick to stabilize the system itself. The solution is an analytical solution is quite tricky, and essentially there is an attempt to do this solution, to solve this equation in a linear term. It's not particularly interesting in terms of the results, but what is interesting for this kind of analysis is the stability. We can look at the stability of the linearized solution, looking the phase space given by alpha and delta. Alpha is the ratio between A and B, and delta, or delta prime, which is the adimensionalized variable related to the time delay. So it is delayed without any physical dimension. And we can divide our phase space in two parts. One that has a stable solution. The other one is oscillatory solution. What does it mean? If the choices between the ratio between A and B and the delay can define once forever the long-term behavior of the solution of this model. And for low delay and high alpha, the solution is stable. So whenever it is the initial condition, the the solution converge on the long term on a single equilibrium. While if you are in this part of the phase space, so for the couple of delta and off alpha here, all these points correspond to an oscillatory behavior of the solution. So the line that you see here has defined the horizon above which the stability the solution is oscillatory, and below the solution is stable. What we interpret, if alpha is B over A, B over A is generally is negative. And because the negative feedback is mediated by Kelvin-Rossby waves. And it will be less important than the wind driving effect. And this means that most probably unstable model for larger B. And what we learn for that. And the oscillation is due to, or is essentially related to the wind and the positive feedback that the wind imparts to the system, and in particular to the SST along the Peru coast. And the other quite important issue is the importance of the negative feedback on the delight damping. If B is 0, we don't have any oscillation. So to have an oscillation or oscillatory solution, we do need some negative feedback connected to delayed damping. This kind of model is not realistic as a toy model, but can give some, well, important and conceptual advance in understanding why the system behaves as it does. This is a linearized analysis, so we capture only part of the complexity of this even simple equation. And we can move further, moving from analytical solution to numerical solution. And what you see here, there are 3 different realizations of the full nonlinear linear equation solution done by numerics. And essentially, this analysis made by looking at numerical solution are in agreement with the conclusion drawn from the linearized analysis. That's quite good. And I had always some problem in looking at this graph, and spent some time to understand, but I didn't find any other more clear graph than this one, because the period gets longer for longer delays. But you see here, delta is the delay, and seems that the period here is longer than here. So as a first glance, I would say that a smaller delay gives longer period. However, you have to look at the scale. The scale is adimensional, so the time is adimensionalized by dividing by delta. And if you look at that, if you multiply this by delta, you will see that the period, the dimensional period of this oscillator is longer than this one. And the periods are 2 to 5 times the delay, non-dimensional delay. And if we took the delay as the scale of the Rossby wave travel time, order of 8 months, roughly. Well, we can have a period of 2 to 4 years, let's say 5 years, 4 years. In practice, we have the events on 2 to 7 years, El Niño events. So keep in mind that we have a very simplified physics included in this equation, and we are looking only on the temperature on the Peru coast. This is quite a simpler local description of much more complex process. And having this said that, so the conclusion of or the explanation of the period is quite in good agreement with reality. So I was really surprised when I saw that, and this is quite a good solution. My major criticism to this model is the fact that we assume the two system as the system as an oscillator. So while we saw in the opening of this lecture, then the two systems, the El Niño and La Niña, tend to self-stabilize. So I'm not so sure that an oscillator or delayed oscillator is a good conceptual model for a more advanced understanding of the phenomenon. However, as a first step, and to look at the importance of the delay and importance of the wind stress, well, this is quite an interesting tool. So we are, from the analysis of a simplified or linearized version of the delayed oscillator model, we understand that wind-driven the Walker self-circulation is a safe amplifying mechanism that is important to define the solution, and for realistic definition of the negative feedback and the positive feedback, we see that the solution that we found will be an oscillating one. So we are far from the stable solution, and the delay play a major role in defining the frequency. This is more or less what we learned for that, and it's quite enough for a quite simple yet mathematically complex system. Now, I have a good, well, I had a good basis of modeling. So I like models because they shed light of the mechanism, even if we are not able to solve analytically the equation, numerical solution can approximate the reality in pretty well, and also can give the modeler a tool that can be adapted and with the due complexity in order to capture the key processes that we have understood from the physical analysis of the results. So if we move from a very basic formulation where the hypothesis is the system is an oscillator, well, the next step is to go towards something that has not this as a basic hypothesis, and can resolve to a shallow water reduced gravity model. These are the momentum equation here for the two components, the zonal and meridional component of the velocity. This is the time derivative of the component. This is the Coriolis term. The Coriolis term here is approximated through the beta plane, and as I told you, one of the most common approximation made here is the fact that since Coriolis is no longer effective, is zeroed at the equator, what can have a major role is its gradient. In Rossby waves is the gradient that matters, not the value itself. So we substitute here the Coriolis term expressed in terms of a linear approximation around the equator. And this is the formulation we capture here. This is nothing more than the reduced gravity term and the derivative of H. This means this is a pressure gradient due to changes in H. H is the layer depth, and this is a dissipation, generic dissipation, a damping coefficient. It's a very crude representation of the mixing, and this is the wind stress. As you see here, we have a simplified model where the third dimension is lumped. We integrate vertically the equation, and so H is no longer present here. Only in the pressure gradient H is present. H represents the layer depth. In this sense, we can, having as a prognostic variable H, we have the possibility to reproduce the variability of what is the thermocline. Can choose H as the homogeneous upper layer, and H is the thermocline or pacnocline better depth. While in the rest of the ocean is not active, is quiescent. And that's why this model is called quite frequently 1.5 layer. One active layer, the other one is passive one, is not considered. And H is the water, is the depth of the upper layer. The second equation we need is continuity that relate the divergence of the velocity here integrated over H that is balanced by the changes of the layer depth. And this means that the fluid is homogeneous, and that the density is also constant and is no longer present here. So you have a very uh, simplified set equation that, moreover, is simplified, assuming for the zonal part the geostrophic balance. So the pressure gradient is counterbalanced by the Coriolis term. This set equation, however, includes you have advection, you have continuity. And in the delayed oscillator model, we didn't have any physical explanation for that. There are justifications for the choices of A and B parameter for the delay, but per se, there were not dynamical meaning of the equation. Here instead, we started from well, substantial simplification of the conservation of momentum and mass. So the physics here is assumed to be much sound that in the previous case. And so we expect more complex, more sophisticated equation. However, the problem is that we are not able to solve it analytically. So we have to resort to a numeric integration. And we'll see during this in next slide the evolution of the H, so the thermocline depth in idealized system where Gaussian hump in the thermocline is exerted by an external forcing. So the initial condition for us is a perturbation in H at the more or less in the western part of the integration domain. The forcing you see here, we'll see better in the next slide, but you see here the initial condition is a sort of anomaly, positive and negative, present here in this area. And negative means that you have lower H, and the red one is higher H. So the thermocline gets deeper with the red and shallower with the blue. And we have the possibility with the above equation to represent properly Kelvin waves and also Rossby waves. And let's give a look at the evolution of this Kelvin-Rossby waves interaction. And as I told you, we have the T0. We have a zonal wind stress anomaly that is transferred into modification of the or perturbation of thermocline. We have nominal time scale, and these are days. And the system can propagate the energy westward in terms of Kelvin waves that are downwelling. So the red, as I told you, means deeper H, or a higher H means deeper thermocline, while the upwelling Rossby waves, which are a bit off equatorial, of equatorial Rossby waves that has a two cyclonic, say, pattern. So two positive of equatorial pattern moving westward. And equatorial, after 50 days from the beginning, the equatorial Kelvin waves has reached the eastern boundary, while the Rossby wave is on the fly, yet on the fly. And at the eastern part, you see that the reflection begins, while the on the western side, the Rossby waves is approaching its boundary. And as you saw, the topography of the basin is respected here in a very crude way, but is respected. We have a sort of South American coast, and here we have the Australian coast present here. This is important to shape geometrically the response. And after 100 days, the Rossby waves reaches the western boundary, while the Kelvin waves here begins to propagate poleward here in form of coastal Kelvin waves. Here the process is better. Here you have a reflection of the Rossby waves in terms of Kelvin wave, and the polarity is the same. So a Kelvin wave, a negative Kelvin wave, before. So the thermocline is shallower here, and there is a superposition of incoming and outgoing waves. So the Rossby wave is still approaching, but part of the wave is already reflected and superposed for that. And on the eastern side, we have the Rossby wave, positive Rossby wave, that is moving westward again. After 275 days, we can still a more complex issue. You can still identify the tail of the original force of the Rossby waves is a reflected Kelvin waves, and the Rossby wave generated by the reflection of initial force Kelvin wave. And the system is oscillating this way, and the onset of the waves is a result of the solution, a numeric solution of the equation that has not included this oscillator as a hypothesis, but this is a consequence. And we see here that the system is quite effective and probably is faster than reality in propagating waves along the basin. And the equatorial ocean timescale adjustment is quite smaller compared to the period of ENSO. And if you have more reflection, at the end we obtain something which is more similar to a La Nina condition, which means that any perturbation ends up on the long run in La Nina condition, which is probably the steady state for the ENSO phenomenon. And in this model, what is missing is the connection with ocean-atmosphere coupling. And this probably is the origin of the longer time scale for ENSO. And here we have listed only the ocean contribution and variation in the thermocline depth. We didn't say anything about heat content, and obviously heat content has a scale which is longer, and the complex ocean-atmosphere interaction also matter and play a role in prolonging the time scale to what is more realistic. I mean, 2 to 7 year period, which is the typical time scale for ENSO. Okay, these are models. We are learning a bit on the very essence of the physics behind El Niño, La Niña. But to proceed to improve either the theoretical and numerical advancement in studying this crucial phenomenon for science and for society, we do need more data. And there is an effort supported largely by the US, which is called the Tau Triton program, has the ambition to keep monitored a huge number of stations or sites along the equatorial Pacific. And you see here, each dot is a buoy, which collects automatically meteor-marine variables that are daily transmitted and disseminated to a researcher and forecaster around the world. So this is good for improved model, good to improve the understanding, but also to improve the quality and the skills of the forecast models for ocean and atmosphere. So atmosphere is also, the meteor forecasts are depending on the medium scale to the on the El Niño state. So having a good and realistic observation rate in place can correct and improve the predicting skill of the model. And this is not the whole story, because we have also satellite that can give the information that, but satellites are only surface, have high resolution. But we do complement the two of them in order to have the better picture of what happened at the El Niño. By the way, the importance of the equatorial dynamics on the global weather scale, and is so well acknowledged that similarly less complete, less extensive, can be found also in equatorial Atlantic, and is the Pirata array, and also an Indian effort for the Indian Ocean, which called the Rama network. Both of them try to capture the equatorial dynamics, even if the dynamic is not similar to the Nino. Say Nino is peculiar, but still they're important. The equatorial dynamics at the ocean or ocean atmosphere interaction is so important for the global scale that the effort is paid not only for science but also for societal issues. We talk about Nino, but Nino is well, quite a descriptive way of approaching this phenomenon. It's been, we talk about Nino in terms of pattern, in terms of area, tongues, and so on. There are, or there's been many attempts to propose indexes or indicators or quantified that quantify precisely the state of the system with a single number. We already saw the Southern Oscillation Index, that is the pressure difference between Tahiti and Darwin. And many different indexes have been proposed. One is the Nino 1+2. This one is then the surface anomaly that is related to the region that often first warms during the onset of the Nino, so anticipates a bit the Nino condition. Then you have the El Nino 3, this red area, which has the largest variability in SST over an average El Nino cycle, ENSO cycle. So the signal is stronger. Then you have El Nino 4, which is the anomaly here in temperature are most highly correlated with global weather pattern. So if you look at the effects on the global weather, so Nino 4 is your index. And another one, which is quite popular, is El Nino 3.4. It is dubbed this way because the area is in between on El Nino 4 and El Nino 3, and is highly correlated with eastward shift of convection. And El Nino 3.4 is highly correlated with the Southern Oscillation indexes. So we have one phenomenon, we have different indexes. We have another one we mentioned is the cold tongue index that just includes the Equatorial Pacific SST anomaly that is strongly connected to the soil. This is our, just to, well, put the complexity in a single frame. Let's move from, well, data to model again. And one of the we saw in last lecture that we had a number of better the one moment please. ENSO pattern has a important influence on the weather condition of a vast area around the Pacific coast, but also in Africa and also in um, other parts of the world. And this kind of teleconnection is can have or can bring disruptive events in a vast part of the United States and in South America and Australia areas. So the capability to predict in time the variation or the perturbation due to El Niño has a very prominent impact on the capability to mitigate these effects if the predictions are available with a substantial anticipation. If you have in advance good prediction, you can take appropriate measure to reduce the impact of the adverse meteorological events. How the system works. Now we have a forecast that spans the seasonal scale. The weather forecast you have available for an, daily or weekly forecast are obtained a different way, are one or a limited number of models that are lumped together in a statistical way, or even a single deterministic model that gives your weather forecast. Here, you have to go longer in time, so the uncertainty associated to the nonlinear process, to the deterministic chaos included in the equation of the model, of the meteorological model, prevent the possibility to predict the weather, but the tendency of the system can be extracted by a careful averaging of different kind of seasonal forecast. We can evolve in time from present condition onward for some months in order to produce not a single prediction, but a plume, they say, a beam of different seasonal forecasts for ENSO. And we can have two different approaches. One is purely statistical. The other one is dynamical as a result. We can just solve the primitive equation, momentum, continuity, density, temperature, salinity, and so on. And you can solve in the dynamical equation. The alternative approach is to exploit the statistics that can correlate present situations to the future and use this as a modeling tool for a seasonal forecast. At the end of the story, you can have a number of different models, more than 20, and then you put this model together and you do careful statistical ensemble regression in order to put together and in order to estimate the probability forecast generated using all the models considered in the plume. And you see here, you can have, the March, April, May, April, May, June. So there are 3 months lumped together. And the probability of the different events are plotted here in color. Gray means no El Niño, no La Niña, so trans Niño conditions. Red is El Niño, blue La Niña. In this season of the prediction for the 2020 is largely no evident signature of changing compared to the, let's say, equilibrium state, no El Niño, no La Niña. But if you should have a change, should be more toward El Niño. From August onward, the probability of La Niña gets stronger and stronger, and the other two tend to decrease. When you go almost 10 months ahead, the three probability are more or less the same. What does it mean? It does mean that the predicting capability of this statistical ensemble regression tends to be negligible. So we don't have any specific information. And this curve, the gray curve, is the curve that essentially shape the climatology. So if you have the climatology, you can say more or less similar things. The climatology for the no El Niño, no La Niña, and the two are the climatology for El Niño and for La Niña. Red Niño, blue Niña. And explaining capacity of the model is higher than climatology until starting from March to April, and is similar to August to September. From March to September, the prediction are good, since are more significant than climatology. And later, more or less climatology and the prediction has the same kind of content. Again, we have to say that this prediction can start, especially the dynamical one, from the observation. The good observation network can give the right initial condition to evolve the dynamical model and to predict the statistical ensemble that they use to do this kind of answer probability. And why? And the lower, the more conservative component of the ENSO system is the ocean. And to have a good objective ENSO probability forecast that has some explaining capability, must resort to having a good description of the ocean, and especially the upper layer in the Equatorial Pacific. That's why observation are as important as a model to give a good prediction of the ENSO system at the seasonal scale. I would stop here, and I'm sorry for the technical problem. I had some problem in running my presentation. As usually, I will send the slide in PDF, and I hope in a couple of days also I'll give you the first issue of the lectures, and but I have to work a bit on that still more, and this first version will be updated later. Don't take too seriously. If you have comment, you find error, they are for sure, or they're unclear part, please refer to me, and both in terms of, for the slide and for the text. This will improve the course for the future student, but is also good for you to clarify doubts as you may find it, and feel free to contact me by email as your convenience. Thank you for the attention, and see you on Friday. Okay.
Thank you.
Thank you.
Thank you.
Ciao.
Ciao ciao. See you soon. Bye bye.